To the cloud. Here we go. So we did a good job watching the video of blowing up a high mass star. Let's blow it up some more right now. So this is a very nice figure, really, that I broke into multiple parts because otherwise it would have been tiny, tiny, tiny. Um, that goes through the steps of how a massive iron core, a massive star iron core, creates a supernova explosion. So remember that we've got this onion model, so to speak, where you've got at the final stage where the star has got hours to live, silicon and sulfur fusing into iron 56. Really, silicon burning first produces cobalt 56, but that's an unstable isotope that decays into iron 56. What's distinctive about iron 56? What's special about that particular isotope and element? Most stable nucleus, right? So that any reaction with it, breaking apart or fusing, is endothermic. It takes energy instead of giving off energy, can't serve as a nuclear fuel. So the silicon fusing shell, we usually call it just the silicon burning shell, keeps adding fresh iron to the core, and it's getting more and more massive. And as we'll learn in the next chapter when we study white dwarfs, essentially what's in the center of the star right now is an iron white dwarf instead of a carbon oxygen white dwarf like a low mass star would be. You got what amounts to would be like if you could strip everything off of it. You can't, but if you could, it would be like an iron white dwarf supported by electron degeneracy pressure. But there's the maximum mass that electron degeneracy pressure can support. Why, it's named after the famous Indian physicist whose name Anushka will correctly pronounce for us right now, Chandrasekhar. And so that limit, it actually would depend on the isotope that the star is made of. That it's not like 1.44 solar masses. When the core gets too massive for electron degeneracy pressure to support it, then it will start to collapse as a result of that. And so not even electron degeneracy pressure can stop the collapse of an iron ash core. And so as the core collapses, what's going to happen to its gravitational potential energy? If it's collapsing, is it increasing or decreasing its gravitational potential energy? Think carefully. If so, it's doing the same thing that happens to this eraser when I drop it. If I drop that eraser, what's happening to its gravitational PE? Going up or going, yeah, going down, right? The core is losing gravitational potential energy as it collapses. And so that's going to turn into thermal energy, right? And so, in fact, a supernova, it's important to realize, is gravity powered. It's not nuclear powered, it's gravity powered. It's the release of gravitational potential energy by the collapsing iron core in a split second that powers the supernova explosion. So, as the core collapses, the core temperature climbs so high that thermal gamma ray photons, just thermal radiation, that it's such a high temperature you got gamma rays in this thermal radiation, they have enough energy to photodisintegrate iron. That's a good word, isn't it? Photodisintegrate. In other words, they have so much energy, they can break iron 56 nuclei apart. And what it mostly does is break them into a bunch of helium nuclei, alpha particles, because that's a very stable nucleus, right? Alpha particles. So if you think about it, the star has spent millions of years building up an iron core, and then when it collapses, in an instant, it undoes all of it. Photodisintegration initially breaks all those iron nuclei apart into mostly alpha particles. And the core becomes so dense that electrons are absorbed by protons in atomic nuclei, forming neutrons and releasing neutrinos, right? So we've talked about this reaction before where you can have a neutron, a free neutron will decay into a proton, right? So you got like neutron becomes proton plus what else comes out of that? So we need to conserve charge. What's the electric charge of the neutron? What's the electric charge of a neutron? Zero. That's because it's a neutron. That's why it's called a neutron, right? What's the electric charge of a proton? +1, right? So what do we need to balance that out? We need an electron, right? We need an electron, but are we done? No, because what's the lepton number of that neutron? 0, right? What's the lepton number of that electron? 1. That's +1. It's defined to be +1. We need to conserve lepton number. Are we done conserving charge? Yeah, we've conserved charge. 0 and 1 plus -1 is 0. We have conserved baryon number because neutrons and protons are both baryons, but we still need to conserve lepton number. So we need a chargeless lepton, an unelectrically charged lepton with a lepton number of -1. So what is that? That's an anti-electron neutrino. So we need a new E bar, an anti-electron neutrino, right? So that is an allowed reaction. And you can move things to the other side. And the sort of algebra of moving things to the other side of a nuclear reaction like this is if you move a particle to the other side, you replace it with its antiparticle. So we can move the electron to the other side of the arrow, but we have to replace it with a positron. That's not what I meant to say. No, I'm sorry. We can. I want it over here still. Yeah. What we can do is we can move the neutrino over to the other side of the equation, right? So we've got neutron plus a matter neutrino, not an antineutrino, but a matter type electron neutrino. And it is possible indeed for those to combine and produce a proton and an electron, but we're going to go the other direction here. You can go either way. And so we're actually, in the end, going to say that what happens is a proton can combine with an electron to form a neutron plus a neutrino. And it occurs to me that I should be turning my camera on for the audience at home. So camera, video, there we go. So here's the glorious reactions right there. Aren't they beautiful? Oh, I'm gonna cry. Look at that, right? Maybe you were following along with the audio and you could hear all that too, but there's the glorious reactions right there. That's what happens in our collapsing core. Electron plus proton becomes neutron plus neutrino. This is how you're going to get a neutron star out of this. A neutron star is mostly a big ball of neutrons. We'll study them in more detail, again, in the next chapter, which is about the degenerate remnants of stars. For low mass stars, the degenerate remnant is a, what's the sun going to leave behind? A white dwarf supported by what kind of pressure? Electron degeneracy pressure. This is going to leave behind a neutron star, which will be supported by instead neutron degeneracy pressure. How big is a white dwarf? Approximately the size of what familiar object? Earth. Oh, yes. Earth, right? How big is a neutron star? Do you remember? Have you learned that before? Yeah, more like a city or a county, something like that. Yeah. So even more spectacularly dense, right? Like a neutron star, something like a paperclip has the mass of Mount Everest or something like that. Whereas a white dwarf, a teaspoon has the mass of a UPS truck. It's that kind of, that's what we're talking there. Either way, don't go there, right? It wouldn't be like anything to be beamed down to the surface of a white dwarf, because before you had time to think, you'd be squashed flat and just become part of it. Even more so with a neutron star, right? Just don't bother. What would it be like to be on a white dwarf? It wouldn't be like anything for human. It's just so completely incompatible with human existence. But in any case, so this is what's turning the core into a ball of neutrons, is that electrons are combining with protons and turning them into neutrons. And you get a prodigious number of neutrinos coming out of this. And for a long time, computer models were having trouble getting supernovae to explode, so to speak, right? They're writing code trying to get the model to blow up, and it wasn't working. The computer was not indicating that an explosion was going to happen here. And then it was finally realized that the neutrinos, as was mentioned in the video, while they normally can pass through like a light year of lead and only have like a 50-50 chance of interacting with anything, the material in the collapsing star is so dense that the neutrinos actually play a crucial role in getting it to explode because they do interact and provide the push that you need to accelerate the shock front, the shock wave that goes out and rips the rest of the star apart, which is pretty remarkable. What questions do you have at this point? So yeah, this is coming from detailed computer models, essentially. Um, the Department of Defense actually would fund a lot of this computer modeling because it turns out that, and this is one of these, like, I don't know if I like this, but it turns out that the same kind of codes that can model the explosion of a supernova can model the detonation of a nuclear warhead. And so I knew folks who were working on modeling supernovae who were funded by money from the Department of Defense because then their codes could be modified to simulate nuclear weapons blowing up. On the plus side, it means you don't have to actually blow up the nuclear weapon. You can just kind of, test it on the computer, so to speak. So I guess there's something to be said for that. But just, kind of this connection there that's something to ponder, I guess. All right. So my mousey over there. So next, right. So we're continuing on, right? So we were on step 3 before, and the core becomes so dense that electrons are absorbed by protons in atomic nuclei, forming neutrons and releasing energetic neutrinos. Photodisintegration and electron absorption rob the core, rob the core, rob the core. Well, that does happen, unfortunately. Yeah, it's anti-Robin Hood here, right? And rob the board and give it to anyway. Photodisintegration, electron absorption, rob the core pressure support because it was held up by electron degeneracy pressure, and this is eating the electrons, and so we're losing pressure support. The photons were not hurting the pressure support either. They're getting taken out of this as well. So the collapse accelerates. Gravity's even more winning this battle now. The core begins to collapse because gravity tips the balance and exceeds pressure within the core until nuclear forces suddenly become repulsive. So the idea here is that once you get to the point where the nuclear particles are essentially nearly overlapping themselves, then it becomes essentially almost incompressible. Really, neutron degeneracy pressure is taking over. The core becomes essentially like a giant atomic nucleus, if you will. So one thing we often don't think too much about is that most of your mass is in your nuclei. All of your electrons put together weigh like, ounces or, grams, but most of your mass is in your nuclei. Let's see, what's the size of an atom, roughly speaking? How big, roughly, is a hydrogen atom? Why, you should know these numbers. I'm sure somebody is about to blurt it out confidently. An atom is approximately what size? 10 to the minus 10. Yeah, very good. About 10 to the minus 10 meters. So 0.1 nanometers. Also called an angstrom. Typically these days we say 0.1 nanometers. So 10 to the minus 10 is about the size of the electron cloud for an atom. It varies from one atom to another, but all atoms are kind of roughly the same size because as you add protons in the nucleus, they're attracting the electrons more strongly. And so that doesn't completely cancel out. But 10 to the minus 10 meters is a typical atomic scale. That is what about the size of a hydrogen atom. So consider a hydrogen atom, right? 10 to the minus 10 meters across. How big is a proton? What about the size of is a proton? So length that's sometimes called the Fermi. It's also called a femtometer. 10 to the minus what power? 10 to the minus 15. Yep, a nuclear scale is about 10 to the minus 15 meters. What fraction of 10 to the minus 10 meters is 10 to the minus 15 meters? Whoops, a little more. Right, it's 10 to what power, right? 10 to the fifth, right? So the atom is 10 to the fifth times larger than the nucleus in the middle. 10 to the fifth is 100,000, right? 100,000, right? 1,000 is 10, right? 10 to the 4 is 10,000, 10 to the 5 is 100,000. So the atomic, so the atomic nucleus has about 10 to the minus 5 the size of the atom of the whole as a whole. What about the fraction of the volume that it occupies? What do I have to do to that 10 to the minus 5 to get the volume fraction? Got to cube it, right? 10 to the minus 5 cubed is 10 to the minus 15th power, right? So most of your mass is in your nuclei. Most of your volume is electron clouds of your atoms and molecules. Most of your mass is in your nuclei, which have only about 10 to the minus 15th power of your volume. So most of your mass is concentrated in 10 to the minus 15th power of your volume. Put another way, what that means is an atomic nucleus is about 10 to the 15th power times denser than everyday matter, if you like. I mean, we're full of atomic nuclei, but in other words, if you find your average density and compare that to the density of your nuclei, well, most of your mass is in those nuclei, which are only about 10 to the minus 15 of your volume. So if you want to find the density of your nuclei, right, you take your mass and compact it into 10 to the minus 15 of your volume. In other words, atomic nuclei are about 10 to the 15th times more dense than the average density of the everyday objects, including our bodies, that we have around us. Does that make sense, that argument there? Somewhat. Okay. All right. So I'm going to say it again. I'm going to say it again. Okay. Think your body, right? What would you do to find your volume? I'm sorry. What would you do to find your density? Your density is your what divided by your what? Mass over volume, right? So you could well, what's my volume? Well, I don't know, right? But how could you figure out how could you measure your volume? What would be a way to do that? No, but I mean, how would you measure it? How would you give me a procedure where you could actually determine your volume? Yeah, get a tank of water, submerge yourself, and see how much the water rises, right? How much water do you displace? So you could measure your volume by stepping into a tank of water, see how much the water level rises. That's how much you displaced. And then you step on the scale, and then you say, wait a minute, that's the force. I'll turn that into kilograms, right? And so you take your mass in kilograms and you divide by your volume that you found from stepping into that water tank, and you say, that's my average density. But it's just your average density, right? It's just your average density, your overall mass divided by your overall volume. But now let's think about, well, where is most of that mass? Okay. Well, if you collected all of your nuclei together, don't do that. You've made a little miniature neutron star. Don't do it. But if you imagine collecting all of your nuclei together into this tiny little thing, it would have most of your mass, but a fraction of 10 to the minus 15 of your volume. So don't do this. You put that in the swimming pool or whatever, and it's hard to measure how much water it displaced. 10 to the minus 15th of the volume of your entire body. So the density of your nuclei is essentially almost all your mass, because electrons are 2,000 times less massive roughly than neutrons and protons are. So it's practically all your mass, but in 10 to the minus 15 of your volume. Most of your mass is in those nuclei. That's 10 to the minus 15 of your volume. You take your mass and divide that by that volume. That's therefore about 10 to the 15th power more than your mass divided by your overall volume. So, in other words, we're not mostly empty space, but we're mostly just fuzzy electron clouds that there's not a lot of mass there because electrons aren't that massive. We're mostly just fuzzy electron clouds with little nuclei in them that are miniature neutron stars, if you will. I mean, not literally, but they're as dense as neutron stars, or turn it around, a neutron star is as dense as an atomic nucleus. And in a sense, it's like it's a giant atomic nucleus, if you will. Giant as in, like the size of a city, but that would be a big thing for a nucleus, right? You got something that is as dense as nuclear matter, but it's the size of a city. These things are amazing. And that's what this thing is producing after the iron core collapses. And so it's incredibly dense, 10 to the 15 times, right? So 10 to the what do we call that number in the US, in the UK and other places? They use a different system, but we say 10 to the 6 is a 10 to the 6, we call that a million. 10 to the 9 is a billion, and except if you're in the UK, it's 1,000 million. Or like, yeah, yeah. So they can get to bigger numbers this way, but we'll stick with a good old American system here. 10 to the 9 is a billion. 10 to the 12 is a trillion. One more up, 10 to the 15 is a quadrillion, right? So a neutron star is about a quadrillion times denser than the Earth is. Yowza, right? Don't go there. Hang out, just look from afar. You can't go there, right? You could not, well, yeah, you could land on the surface, but you wouldn't be you by the time you got there, okay? So, yeah. So when it reaches that kind of density is when the collapse is going to bounce back, is what it comes down to. So it's collapsing, it stiffens when neutron degeneracy kicks in and rebounds. Well, the collapse is like at a quarter the speed of light. So then it rebounds at like a quarter the speed of light. Meanwhile, there's this material crashing down on it at those kinds of speeds. Well, you can imagine this could have some consequences, right? And coupled with the acceleration provided by the neutrino kick, it does. It creates a shock wave that tears through the outer layers of the star. It actually takes a few hours to get to the surface where you would actually see the supernova happening. And in fact, the first thing we see from a supernova, if we're looking, is the neutrinos. In 1987, in Cleveland, neutrino detector outside Cleveland saw, I think it was a dozen extra neutrinos than normal. But if you see that, say you have these big tanks of like dry cleaning fluid, because they suck at detecting neutrinos, but they're better. But they're better than other things. So we use that to detect neutrinos. Oh yeah, Cleveland, right? Anybody else from Cleveland here? Yeah. Oh, Cleveland rocks. All right. So that's where I went to Case Western Reserve, right? So there we go. Yeah. Anyway, they see like a dozen extra neutrinos, which implied way more than a dozen. Actual neutrinos were streaming through the Earth, right? If you find 12 neutrinos with that detector, there was way more than 12 neutrinos that were swarming through Earth at that moment. And then not long after, they see supernova 1987A going off, and a beautiful proof that we know what's going on when a supernova goes off, a core collapse supernova, because you would predict you'd first get a burst of neutrinos because those get out first, and then later the shock wave reaches the surface of the star, and the outer layers that are all collapsing inwards, and creates the explosion that we see, where we'd actually see something. So beautiful. Until nuclear forces suddenly become repulsive. I know we already said this, but we're continuing here. The overcompressed core bounces, driving its outer layers outwards through the star. The expanding shock is strengthened by the pressure of a hot bubble of trapped neutrinos from the core. Most of the energy is actually in the form of neutrinos from the collapse, but they're hard to notice once they get out because neutrinos are terrible at interacting with other things because they only interact via the weak nuclear force and gravity. The shock continues through the outer layers of the star, blasting forth in a type 2 supernova. And of course, remember, right? I can't possibly say blasting impressively enough to convey what this thing is doing, right? So remember from the video from XKCD, I'd never done that calculation before, right? So I've seen the numbers and I'd never really fully appreciated that. Wow, the sun will never blow up as a supernova, but if a supernova went off, the sun's distance from us, that would be 1 billion times more energy passing us as you get right. Yeah, put your head in that blast of a supernova 1 AU away, put your face on a nuclear weapon and detonate it in your face, and the supernova's like more than 1 billion times worse than the nuclear weapon that you just detonated in your face. Oh my, yeah. So blasting, right? Blasting! Except I have to have just, vaporized everybody, right? Blasting forth in a so-called type 2 supernova and leaving behind the collapsed remnants of the core. A neutron star. Next chapter, we'll talk more about neutron stars. But there we have it. We made us a neutron star. We can also get black holes. I need to check on this, though, because it seems like we're thinking more and more that at least many core collapses that produce black holes don't make supernovae. It's more direct. You just make a black hole. I mean, there's also stuff that comes out in beams and stuff, but at least kind of a classic type 2 supernova neutron star comes out, which is impressive enough. There's 3 possible remnants of a star: white dwarf, neutron star, and black hole. And I mean, one is more exotic than the next, is what it comes down to. Okay, questions? Yeah, yeah. So this is what I mean when I say that, someday Beetlejuice is going to blow up good, right? We're really talking about blowing up good here, such that even at our distance of like 600 something light years, you see it in the daytime when this happens. It's like be about as bright as the full moon, but concentrated into a brilliant little point. Much as I love Beetlejuice, I want to see it blow up. Blow up. Of course, it's either still, in our frame of reference, it's either still just being a red supergiant. And if that's true, well, we ain't going to see it because it's like 600 light years away. So, but if we are going to see it, Betelgeuse is actually already a neutron star, and we just don't know it yet because the light from the supernova is on its way here. So if we're going to see it blow up 10 years from now, 10 light years away from here is this blast of photons and neutrinos heading our way, right? That we'll see in 10 years. Except you can't know it until you see it. So it might be, nope, Betelgeuse is still there and we're not going to see it blow up. I'll be sad if well, I'll never know, but maybe there's this front of photons and neutrinos that's 200 light years away. And Betelgeuse is a neutron star, but we won't know for another 200 years, right? We just don't know, is what it comes to. We just don't know. We can't, right? Crazy to think about, so, right? Tell your friends. Okay? So, a bit more details from the book. I mean, you don't have to memorize all this, but you should be exposed to this and think about this, right? So when the core becomes I mean, some of this this wouldn't be on this exam. I might give you some stuff to know for the next exam. When the core becomes filled with iron 56, we know the star is doomed because any product of iron 56 fusion are more massive than iron 56, more massive than the stuff that went in. So it absorbs energy and converts it into mass. So the sun's out of nuclear fuel. Why? When the core density reaches 3 frickin' trillion, right? Normally you would say 3 times, but when it gets to numbers like this, you pronounce it as 3 frickin' trillion kilograms per cubic meter. Electron degeneracy pressure can no longer support the core, so it collapses. It has reached the... There we go, yes. The temperature soars to over 5 billion Kelvin. How long does that take? 1/10 of a second. Time, oh, we're done already. Gamma rays produced by the extreme heat are energetic enough to break apart the nuclei via photodisintegration. I will want you to know things like what is photo. Again, this is for the next exam. I will want you to know what is photodisintegration, right? What is the reaction that produces the neutrinos, right? You want to know this. And that's a good name too, neutronization, right? That's not your everyday word. When the core density reaches, I think that's supposed to be like 310 to the 15 or something like that. Or no, so yeah, I don't think those numbers are supposed to be the same. We gotta check that. I might know. But anyway, when the core density reaches a really big number, electrons start combining with protons to form neutrinos in a process called neutronization. Electron plus proton becomes neutron plus neutrino. If the core mass is less than about 3 times the mass of the sun, the core collapse is halted by neutron degeneracy pressure when it is about 20 kilometers across, forming a neutron star. The core collapse is so rapid it leaves a gap between the core surface and the layers of gas above. And I always like to think of this, have you all seen like the Wile E. Coyote and the Roadrunner, those cartoons, right? So, you know, when Wile E. Coyote like runs over the edge of a cliff, right? And then they don't fully follow the laws of physics because he'll be like looking down there and like holding up the sign that says help or whatever, right? Now, actually, as physicists, we know that he'll immediately start to plunge over the cliff instead of hovering there for a moment. But this is kind of like, you know, I like to think of, well, there goes the core, and the others are like, help, right? And so these layers soon crash down onto the core surface at a speed of about the quarter of a speed of light, creating an incredibly powerful shock wave that blows the star apart in the supernova explosion, helped by the neutrinos. Peak visible light luminosity is about 1 billion times that of the sun. It rivals the output of an entire galaxy for a moment, which is why you see these photographs and, oh, look, there's a new star in the galaxy, so to speak, that's about as bright as the rest of the galaxy. That's what these things do. Most, however, of the total energy is radiated in the form of, that's supposed to say, of neutrinos. The peak neutrino luminosity reaches about 10 to the 46 watts, or about 10 to the 19th power times the sun's luminosity. Let's see, 10 to the 19th. So we've got to 10 to the 15th was a quadrillion. 10 to the 18th is a, what's the next one? Quad. So that's 4. What's 5? Quint. Yeah, quintillion. So 10 to the 19th, right? 10 quintillion times the sun's luminosity is coming out in the form of neutrinos for a moment there. Holy, right. Again, you know, it's like, why, if you think about this, it'll make your head explode, so to speak, right? Just like the star, except it won't be as impressive. And don't do that, right? Just think about it. Don't let your head explode. But yeah, it's kind of like, right? I can't picture how big an explosion, right? Nobody can, right? But wow, it's impressive. So here is the star that was observed to explode in 1987. which was in a catalog. So I went to Case Western Reserve University, and they had two professors in the astronomy department there, Bruce Stevenson and Nick Sanduic. And they were there when I was there, so I knew them both. And they had cataloged this star. They were catalogers, basically. They made catalogs of stars, and they had cataloged this star before it blew up, which was important because that helped astronomers to figure out a better understanding of the resulting supernova. It was actually underluminous, not as luminous as you would normally expect. And it turned out that it seems that the star exploded when it was in a blue supergiant phase instead of a red supergiant phase. And that meant that it was more tightly bound by gravity because a red supergiant is bigger than the blue supergiant. And so more of the explosion had to expand the star, went against expansion of the star against gravity, and less came out in the form of light and so forth. And the fact that they had cataloged it and given its properties was important. And then what is it? They also got, there was in 1979, there was a very unusual binary with I think a black hole in called SS or something or other, but the SS stood for Stevenson Sanduic. And so they got their names. Like, I mean, Saturday Night Live did something about it. And so it was kind of fun, got their names on things like that. But anyway, sure, the supernova actually appeared as a bright point of light. I think it got to like second magnitude or something like that, like seen from Earth, like Big Dipper stars kind of brightness. But it was in the Large Magellanic Cloud, which is, like something like 160 something thousand light years away. It's a satellite galaxy of the Milky Way. So it wasn't visible from where we are. It was visible in the southern hemisphere. The first supernova that happened anywhere near Earth in like since 400 years. We should have seen more, but the statistics have worked against us. So this is the only recent supernova that was not in a very distant galaxy. We still haven't, with modern instruments, seen a supernova pop off in the disk of our galaxy. But this one was relatively close by. So it was our best example of a nearby supernova. I'll make some more detailed observations of with modern instruments. I'm going to count 1987 as the modern era. And if you argue with me, well, go to anyway. So the supernova actually could have appeared larger than a point in this photograph. It's just an overexposure. It would look like a point of light, but you see it to the naked eye. And that's one of those things like, it's like, I don't remember that star. Wait a minute, so people are like, wait. So people are like rushing to report, because you want to turn all your instruments to this as quickly as you can, because you're wasting time. Supernovae are relatively brief. You want to capture as much as you can. Now let's talk about, well, first I'll just stop and say any questions at this point, comments, observations. CJ, I thought were you raising your hand before, or were you just like, I don't know. Yeah, okay. Right. All right. So you're seeing my coat. Hello. So that'd be weird, just like this little thing up in the corner. Okay, anyway. I should just extend that. No, I'm not going to do that. Anyway, okay. Just keep enjoying the blackboard. It's beautiful, isn't it? Actually, I'll just turn off the video. I could also do that. Okay. I want to talk about just kind of, nucleosynthesis in general, right? Everybody should know, and a lot of people do know these days, that where are the chemical elements formed, right? Well, stars in various ways. What came out of the Big Bang? What elements came out of the Big Bang? Hydrogen and helium. Most of the helium in the universe is primordial. It came out of the Big Bang. Yes, stars are making helium today, but that's just a small fraction of the total amount of helium in the universe. Most of it is primordial, left over from the Big Bang, a brief burst of nucleosynthesis when the universe was a few minutes old. Virtually everything else. So some lithium came out of the Big Bang, but And beryllium and boron are made in interstellar spallation reactions, but essentially everything is made in stars one way or another. One of the most profound revelations that humanity has ever had. I think I might have told you before, and if I didn't, I'm telling you now because I forget. Once when I was teaching intro astronomy, the next class was intro chemistry. And I asked the students, where did all these chemical elements you're studying come from? And they didn't know the answer. This needs to be fixed, right? Everybody should, especially people think they came from stars, right? We're not figuratively made of stardust. We're literally made of stardust. Why are rare earth elements rare? Why are they called rare earth elements? Because those elements are not very abundant in Earth's crust. So they're rare as a result of that. Well, fundamentally, what makes an element rare? How would you answer that question? An element is rare if it is what? Hard to make, not on Earth. Where do the elements come from? Stars. So an element will be rare if it is hard for it to be made in stars. Hard for it to, right? The elements that are rare are the ones that are hardest for stars to make via the nuclear reactions that are happening within them. Rare earth elements are rare because stars have a hard time making them, right? So there are fingerprints in the abundances of elements of stellar nucleosynthesis. It is not a solved problem. We don't have a complete description that can explain the details of the abundances of all of the chemical elements, though we have made a lot of progress. But that is a topic of study, is can we explain the relative abundances of the various isotopes that we see in nature based on stellar nucleosynthesis, right? So one type of reaction that occurs, which isn't a primary energy generating sequence, but there are, we talked about these primary fusion stages of stars, like carbon fusion, oxygen fusion, all this kind of stuff. The primary energy generating reactions, but those aren't all that's going on, right? In the milieu of a stellar core, there are lots of side reactions going around that are contributing to the synthesis of the elements that we find in nature. And one particularly interesting and important sequence are helium capture reactions, which are exactly what they sound like. A nucleus captures a helium-4 nucleus. What do we call a helium-4 nucleus? Another name for that is an alpha particle, right? So there's alpha capture reactions. So a carbon-12 nucleus can fuse with a helium-4 nucleus and make oxygen-16. And we know white dwarfs have some oxygen-16 in them because helium fusion via the triple alpha process, you can also get another step where later on a helium-4 fuses with a carbon-12, makes an oxygen-16. But oxygen-16 nuclei that already exist in a star from earlier generations can also participate in this fun. Why an oxygen-16 can capture a helium-4 nucleus. You add 2 protons and 2 neutrons, you get neon-20, 10 protons, 10 neutrons. And that can capture a helium-4 nucleus to make magnesium-24, 12 protons, 12 neutrons. So you've got magnesium in you. Where did it come from? That inside stars, right? It's just wow, and so and well, I guess I'll go ahead and talk about the bottom one before I get to the next slide because I want to say something about the helium capture reactions. Here's some other reactions. Why a carbon-12 and an oxygen-16 can form silicon-28. And 2 oxygen nuclei, 16, can fuse to form sulfur-31 because it also spits out a neutron, and so it has 16 protons and 15 neutrons. 2 silicon nuclei can fuse to make ultimately iron-56, but again, it first makes cobalt-56 that then radioactively decays into iron 56, the most stable nucleus. So these helium capture reactions have a very interesting signature in cosmic abundances. Here are the abundances of elements within the sun, and it's a good reflection of overall cosmic abundances. So careful study of spectroscopy allows us to deduce cosmic abundances. You can't deduce it from studying Earth because Earth has atypical composition, right? In other words, most of the matter in the universe is hydrogen and helium. Earth has very little hydrogen and helium. Earth is not a star, it turns out, which is probably for the best for us. So you have to study stars in order to get a real handle on cosmic abundance of stars, the interstellar medium, stuff that's more primordial composition. And so this is a logarithmic scale, relative abundances, atoms per hydrogen atom. So it looks like there's almost as much helium as hydrogen, but it's a logarithmic scale, right? So if we call hydrogen 1, helium is a bit below 10 to the minus 1 on that. So there's roughly about 10 times as many hydrogen nuclei as helium nuclei. And then it keeps dropping off, right? The next one, lithium, 10 to the minus 10 relative to hydrogen, much less lithium around. There is then beryllium and boron, which are made by cosmic rays hitting other nuclei in interstellar space. Stars are not a source of that particularly. And then you get to carbon. Carbon, you have a jump up in the abundance of carbon. Why would you have a lot more carbon suddenly? Are stars good at making carbon? Yes, they are. They can do the triple alpha process when they get to the helium fusing stage and make carbon. So carbon's relatively easy to make, so it's rather abundant. Not nearly as abundant as hydrogen, right? Less than 10 to the minus 3. There's more than 1,000 hydrogen atoms for every carbon atom. But relatively speaking, fair amount of carbon, a little less nitrogen, pretty abundant, but not as much nitrogen as carbon, and not as much nitrogen as oxygen, which supernovae are good at making. And so it turns out you get a spike in the amount of oxygen too. And then you get a drop to, I should really wait, please, to what's between oxygen. I think it's fluorine between oxygen and neon, if I'm not mistaken. And then you jump up to neon. But anyway, the point is, how many protons in carbon? 6. Correct. How many protons in nitrogen? 7. How many in oxygen? 8. How many in this? 9. I think it's fluorine. Or I think it is. I think it's 4. Yeah, I think it's 4. How many in neon? 9. How many in? I think this is sodium. 11. This is 11. 12 in magnesium. 30, right? So you get the spike up and down. Yes.
For even numbers, there's a spike.
Yes, there's a spike every time you hit an even number, right? Yes, there's a spike every time you hit an even number. Why? Because of the fact that you can make even numbered nuclei via helium capture reactions. Every helium capture reaction adds 2 protons, and it starts with carbon 12. And so you can make even numbered elements, even number of proton elements via helium capture reactions, and you can't, it turns out, make the odd numbered elements that way. And so, at least I'm pretty sure you can. I could be wrong about there's no way to make them with helium capture, but at the very least, I should check that. At the very least, helium capture starting with carbon 12 is the best way, so to speak. So because of helium capture reactions, even numbered elements are consistently more abundant in the universe than odd numbered elements. And again, how remarkable that this signature of stellar nucleosynthesis is present in cosmic abundances. The even numbered elements can be made by helium capture, starting with carbon 12. The odd numbered elements cannot. And so the even numbered elements are more abundant and the odd numbered elements. Break time. Why, Jan, did you have some sort of question?
Well, I do have,
Yes.
what's that gap right there between 40 and 50, there's a W.
Oh, you mean like this gap that would correspond to 43 protons in the nucleus? Yeah. So that's a very astute observation. Like, what's so funny? So anyway, damn, they're gonna figure it out. That's actually technetium, as a matter of fact, because there's no stable isotope of technetium with 43 protons in the nucleus. And so as a result, we generally don't see it. It's extremely unabundant within the universe because the half-life is something like 200,000 years, which is very short astronomically speaking. And so it doesn't last in the interstellar medium. You're not going to see it in the outer layers of stars, except a small number of them where they're having what are called dredge ups, where deep convection reaches down into the core and pulls up nuclear process material. We do see some stars that have technetium lines in them, and that tells us that they are pulling up nuclear process material because the short half-life means that if they weren't doing that, it would just decay and you wouldn't see it in their spectra anymore. And so that's why there's a gap there, which is pretty cool. It's almost like you asked that question at the end of the last period, and I wanted to throw it in right now. Yeah, that's why I was laughing. Leave me alone, people at home. Anyway, so notice that there's also the iron peak as well, again, because, well, it turns out there's this mechanism that stars are able to make iron. We've talked about one of them. Now, actually, a lot of the iron that a massive star makes ends up as a neutron star. But as we'll see when we talk about white dwarf supernovae, they also produce iron. And in fact, you get more iron out of those than you do out of massive star supernovae because that iron shows up. It actually gets blasted into the interstellar medium. So, in fact, here's from Wikipedia a periodic table depicting how the elements were made. And so you see that blue is Big Bang fusion, although for hydrogen, that's not really, I wouldn't describe it like that. It's just came out of the Big Bang. Helium, a lot of it was made, most of it was made by Big Bang fusion. And then there's dying low mass stars is the kind of lime green. And so you can see that lithium and strontium and what is this? I can see terbium and barium. There's a lot of things where dying low mass stars are the primary source of those elements. Exploding massive stars, core collapse supernovae, are primarily responsible for the oxygen, some of the carbon, some of the nitrogen, but most of the carbon and nitrogen are from dying low mass stars. Human synthesis, no stable isotopes. Could there be something here on the periodic table that look at technetium 43 there, why it's made by human synthesis. And you do see it, well, we've talked about that. Cosmic ray fission, beryllium, boron, merging neutron stars. So neutron stars, we'll talk more about neutron stars later. When neutron stars merge, they're not all neutrons. They're well, first of all, they do have some protons in them, about 1/8 as many. There's in the end a ratio of like 8 neutrons for every 1 proton and every 1 electron deep in their interiors. But their outer layers are made of iron, and then actually, like, the crust is made of iron. The deeper you go, we'll talk more about this later, you get these exotic, very neutron-rich nuclei that wouldn't be stable in any other environment. Anyway, when neutron stars spiral into one another by emitting gravitational waves, and merge, you get a burst of nuclear reactions in the material that's in their outer layers. And amazingly enough, that's a relatively recent realization, because we before had thought that the elements heavier than iron came almost exclusively out of massive star supernovae, because remember that to make elements heavier than iron, if you're going to fuse things together, that's an endothermic reaction. It takes energy. So it's not normally going to be made in a star, but during a supernova explosion, in the shock wave, you can force nuclei to fuse with one another, robbing the shock wave of some of its energy. So there are some elements heavier than iron that are primarily made by massive star supernovae, like krypton and germanium and gallium and other things whose chemical symbols. Wait, what's the element again? But anyway, merging neutron stars are primarily responsible for many of the so-called rare earth elements and for the jeweler's elements. So let's see, what is Ag? Remember?
Gold.
No, that one's silver, but Au is gold. Pt is platinum, right? So silver, gold, and platinum are used in jewelry. They're the jeweler's elements. As a Harvard study from back about 12 years ago or so called them the elements of bling, as it were, right? Bling, because that's a slang term for jewelry, you know, like, okay. We now know that they're made primarily by merging neutron stars rather than in massive star supernovae. And so, for example, if you look at my wedding ring here, right, it's made of gold. It's kind of fancy. It's got some impurities in it to make different colors. But anyway, so why is gold precious? Oh, well, one is it's pretty. The other is it's rare. Why is gold rare?
For any elements that you made inside extreme conditions.
Yeah. Right. Which is what you were going to say too, right? Yeah, right. It's made by merging neutron stars. That's not exactly a common thing to happen in the universe. That's a rare thing to happen. Now, it turns out that a pair of merging neutron stars, like in that Harvard study, they looked at the aftermath of a merging pair of neutron stars, which was in another galaxy, like billions of light years away, but we can see it from vast distances. That was estimated to make something like the mass of the moon worth of gold, right? That's a lot, right? But on the other hand, the mass of the moon, cosmically speaking, isn't that large. You spread that into the interstellar medium and mix well, and that's still not a whole lot of materials what it comes down to. So gold, platinum, and silver are precious because they're shiny and pretty, but also because they're rare, and they're rare because they're made by merging neutron stars, right? Isn't that crazy to realize that most of these atoms on my finger here in this ring, they're made from a pair of, well, more than one probably, merging freaking neutron stars billions of years ago, right? That's the kind of thing like, if that doesn't blow your mind, I cannot reach you, right? You know, if that doesn't amaze you, and I know this amazes you, you're my people, but as I tell the intro astronomy students, if this isn't blowing your mind, I give up. I cannot reach you. You're just a very different creature than I am, essentially, right? Appreciate it. Look at iron, right? So iron is exploding massive stars contribute some iron, but most of it comes from exploding white dwarfs. We'll see that when a white dwarf blows up, one way is by having matter transferred to it from a companion star until the interior reaches the ignition point of carbon fusion, 600 million Kelvin. That, because it's degenerate, means temperature doesn't depend on pressure. And so you get something similar to the helium flash. Right. Except this time it's like a carbon flash. And it keeps going. When the white dwarf blows up, you start getting carbon fusion in it, but that can't expand the white dwarf because it's degenerate. So that energy goes into heating the surrounding material, which causes a burn front, so to speak, to propagate subsonically, it turns out, from supercomputer simulations determine this. It had been a question before, is a white dwarf explosion a detonation or a deflagration? A detonation, the burning front would be moving faster than the speed of sound. A deflagration, it's moving below the speed of sound. Turns out it's a carbon deflagration within the white dwarf. And it gets hotter and hotter, and nuclear fusion all the way up to iron occurs. And so, and also it releases so much energy that it blows the white dwarf to shreds, and it makes elements all the way up to iron. And most of the iron in the universe is from that process, from exploding white dwarfs, from carbon deflagration that causes nuclear fusion all the way up to production of iron, seeds the interstellar medium with the remnants. And so I always say, if you cut yourself, well, that sucks, but you're looking at your blood there and it's red. What in your blood combining with oxygen gives it the bright red color? Hemoglobin, right? And hemoglobin, but we're getting there. At the center of every hemoglobin molecule is an atom of iron, right? And where did that iron come from? Mostly exploding white dwarfs, but also collapsing massive stars as well, right? So it's like, oh, that sucks. I cut my foot. Blew up. But the white dwarf blew up to make that. Massive stars blew up to make that. Wow, right? You look in the mirror and you're like, you look at it. Oh, I'm kind of like Rosie today. Oh, look at that. White dwarfs. Massive star supernovae is where that iron came from that's making your blood red like that. So turns out we're kind of connected to the universe. And it turns out I can go over and open the door and I can open the door and grab the cell. I hope. Yeah. There we go. Some exploded white dwarf material right here, right? These atoms used to be, some of them were in a white dwarf that blew up, blew up and formed them as part of the explosion. Some of them were in massive stars that blew up. Wow, right? That's crazy. As I like to say, if your atoms could talk, then they would have such amazing stories to tell. But if your atoms do talk, you should lay off the mushrooms, right? But still, right? It's amazing, just amazing. So look at that, right? Look at that. What we've learned. This is relatively recent human knowledge that we are privileged to be aware of. I really like this diagram because it humanizes it. So I'll just read it. The hydrogen in your body, present in every molecule of water, came from the Big Bang. The carbon in your body was made by nuclear fusion in the interiors of stars, as was the oxygen. Much of the iron in your body was forged during supernova explosions that occurred long ago and far away, actually pretty much all of it, of the two types. The gold in jewelry likely came from neutron stars colliding and may have been visible as a short duration gamma ray bursts or gravitational wave events, as we've seen them. Elements like phosphorus and copper are present in our bodies only in small amounts, but are essential to the functioning of all known lives. And so oxygen is the most abundant element in the human body by mass, not by number of atoms, because oxygen is much more massive per atom than hydrogen is. There's more hydrogen atoms, but there's more oxygen mass because each oxygen has 16 times the mass roughly of hydrogen. But you're about 65% oxygen by mass. Calcium helps form and maintain healthy bones and teeth, and iron is a vital part of red blood cells that carry oxygen through the body. All of the oxygen in the solar system comes from exploding massive stars. About half of the calcium and about 40% of the iron also came from these explosions, with the balance of these elements being supplied by explosions of smaller mass white dwarf stars. So here is U by mass: 65% oxygen, 18% carbon, 10% hydrogen, 3% nitrogen, and other is whatever. And then by where it came from, 73% of your mass came from atoms that were born in exploding massive stars. 16.5% came from dying low mass stars. 9.5% of your mass is from Big Bang fusion, and about 1% is from exploding white dwarfs. Quite the perspective to have, right? Amazing. And I think everybody should know this. So be an evangelist, go spread the word, right? Stop people randomly on the street and say, do you know how much of your mass is from dying, exploding stars? And then they'll be like, whoa, right? But still, do it. Yes.
In the early stage of our solar system, was our area kind of part of the star cluster? Because that seemed like a bunch of different stars dying, and usually stars are far apart from each other.
So right. So the thing is, you don't want to think of us. It's not that your material came from a star. It came from many stars. It's a mixture of material from generations of stars. The interstellar medium has been enriched over time by generations of stars. And so, in other words, in all this mix here, some of this is from stars that died and enriched the interstellar medium far away from where the sun was eventually, born or whatever. But then over time, things get mixed together. It would still be a part of the, like the local region of the galaxy or whatever. But in other words, there was a supernova that appears to have started the formation of the solar system. But that doesn't mean that supernova was the origin of the elements in us. Earlier generations of stars had already enriched the interstellar medium in our vicinity and the rest of the galaxy too, but in our vicinity with nuclear process material. And our sun and Earth was born out of material that generations of stars had enriched. That's the big picture then. Yeah, I feel like I was going to say something else there too, but I can't think of it. Yes. No, the other planets have comparable amounts. It's just that we haven't been to the other planets to find it. But Venus has gold too. It's just that it's not economically feasible to go looking for gold on Venus. Yeah, and Mercury has gold. They all do. It's just that Earth is where we can actually get to it. Yeah, but the overall gold abundance is going to be comparable on the terrestrial planets, to one another. Yeah. Yep. Meanwhile, comets and outer terrestrial worlds, moons of giant planets, the atmospheres of giant planets. In terms of molecules, very common are water. What's the chemical formula for water? H2O. Carbon dioxide, CO2, carbon dioxide, right? Methane. What's methane? It's natural gas, quote unquote. It's what we, but so that's kind of, a common name for it. Methane, what's its chemical formula? Close, but no cigar. It's CH4. Carbon can form 4 bonds like that. CH4. And then there's ammonia. That's the nitrogen one. What's its chemical formula? And H. Yes. There's, you got to be bold, right? No guts, no glory. Glory. Yes. And H3. Those molecules are all pretty common. Why are they so common in light of this slide right here? Yeah, because but also, I mean, not the nitrogen, but it's not like nitrogen is rare, right? So in other words, what's the most abundant element in the universe in terms of the number of atoms? Hydrogen. What's the second most? What's the third most? Oxygen. Fourth most? Carbon. And not quite fifth most, so I say fifth would be neon. Sixth is nitrogen, right? So in other words, the reason why water and methane and ammonia and carbon dioxide ices are very common in the interstellar medium and on icy worlds and in comets, and we have oceans made of water. What's behind that? Because those compounds are made of the most abundant element in the universe, hydrogen, combined with other atoms that are also up there on the abundance scale, right? Carbon, nitrogen, and oxygen are amongst the most abundant types of atoms in the universe. So it stands to reason that those compounds are going to be relatively abundant as far as molecules are concerned, right? Connections. All right. Questions, comments, observations. Right? Go accost a chemistry professor and be sure they know why. And then they might get mad at you, but do it anyway, because I don't want to. Okay. So they might be, well, of course it's stars. What are you, an astrophysics major? Everybody knows that, or every chemist knows that. I hope they would say that. They should say that. They should say, well, of course it's because in the universe. I think chemists ought to know this, and many of them do for sure. Yes. Okay. Let's talk more about supernovae. So the massive star supernovae are called type 2 for a reason we'll get to, Roman numeral 2. There's two types that we subdivide them into, type 2P and type 2L. The P stands for plateau, and this is the plateau. It's not really level, but in other words, after maximum brightness, it decays for a while, the brightness diminishes, and then there's a plateau, as in the rate at which the light diminishes slows down for a while, and then it speeds up again. And then type 2L don't have a plateau. And so then the question becomes, well, why are there some that have the plateau and some that don't? And here's a slide which would break every rule if you're in 498, right? Every rule for slides right there, right? This is, from that standpoint, a terrible slide, but it's actually, I think it's from a website, if I recall correctly, and I just screen captured it. So the reason being this, this will just put it in the notes easily. I don't want to write all this down. So let's just, what's that? Yes, I'm killing you. That's right. Yes. So never make an actual slide. But this is an explanation of what's going on. And we'll just read along here because right. So the peak in the light curve occurs at the temperature of as the temperature of the outer layers starts to decrease. At this point, type 2 supernovae, SN2, are subdivided into two classes based on the cycle of their light curves. Type 2L linear, so in other words, it's more of a straight line on a plot of brightness versus time. Now that's a logarithmic plot still, because so it's really an exponential decay in the flux we're getting at Earth and the luminosity of the star. But we're plotting on the magnitude scale, which is logarithmic. So the exponential plots as a straight line. We use a logarithmic scale on the y-axis. Type 2 linear supernovae have a fairly rapid linear decay after maximum light. Well, type 2 plateau, SN2P supernovae remain bright on a plateau for an extended period of time after maximum. The peak brightness of SN2L are nearly uniform at 2.5 magnitudes fainter than a type 1A supernova. Type 1A are the exploding white dwarf supernovae, and they actually in visible light are brighter than massive star quark collapse supernovae. They're not more luminous overall because they don't produce the burst of neutrinos, and most of the energy in a massive star supernova is in the form of those neutrinos. But in terms of visible light, the white dwarf supernovae are actually brighter than massive star supernovae. However, the peak brightness of SN2P shows a large dispersion, which is almost certainly due to differences in the radii of the progenitors, the stars that gave rise to them. The onset of, so this is fun with radiation transfer, optical depth, all this kind of stuff. The onset of the plateau phase corresponds to a change in the opacity in the outer layer of the exploding star. As the shock wave produced by the core collapse propagates out through the star, it heats the outer envelope of the star to over 100,000 balmy Kelvin, ionizing all the hydrogen, right? At high temperatures, just strip the hydrogen of its electrons. Ionized hydrogen has a high opacity. Why? Why does ionized hydrogen have a high opacity? Ooh, I'm walking towards you, being all threatening. Why does ionized hydrogen? What is the primary source of opacity deep in a star where everything is ionized? Remember? Some kind of scattering. What's scattering the photons as the source of opacity deep inside a star? What's the electron? Yes, electron scattering is the source of opacity in fully ionized plasma. It's almost all electron scattering, so that's what's happening here. Ionized hydrogen has a high opacity, as you all said, due to electron scattering. I was amazed how you all said that at the same time. Probably the people watching at home didn't know, but you all are smarter than me. So sorry about that. Okay, high opacity from electron scattering. So radiation from the inner parts of the star cannot escape. It's well below optical depth 2/3. So photons just can't get out from there. And we can only observe photons from the outermost parts of the star down to optical depth of like 2, 3 or something like that as well. So all the photons are coming from. Of course, with the usual approximations, the layer at an optical depth of 2/3 is at the effective temperature of the star, of the material. After a few weeks, however, the outer parts of the star is cooled sufficiently that the ionized hydrogen is able to recombine to form neutral hydrogen in core collapse supernovae, which are the massive star supernovae, iron core collapses. The critical temperature for hydrogen recombination lies between about 4,000 and 6,000 Kelvin. So so that the ionization temperature depends on the density and so forth. In a star, what did we say the temperature of the ionization of hydrogen occurs at? It's a bit higher. What's the temperature for ionizing hydrogen in more ordinary stellar conditions? It's about 10,000 Kelvin, right? Remember Goldilocks and the 3 stars, right? 10,000 Kelvin. But under these conditions, it's more like 4,000 to 6,000 Kelvin. If you took cosmology, astronomy 260, you may remember about the aptly named, as in not at all aptly named, era of recombination, the first time that hydrogen ever formed neutral atoms after the Big Bang. So the first time it ever happened is called recombination because of astronomers. Did you remember, what was the temperature of that? It's the original temperature of what we now see as the photosphere of the universe, so to speak, cosmic background radiation. It was about what? Do you remember? Yes. 3,000 Kelvin. Why, yes, that's absolutely right. About 3,000 Kelvin. But here we're talking 4,000 to 6,000 Kelvin. While ionized hydrogen is opaque, neutral hydrogen is transparent in most wavelengths. When that happened in the universe, when the universe became neutral hydrogen, all of a sudden it became transparent. And not in a flash, not instant, but cosmically speaking, very rapidly it became transparent. And the radiation was free to fly, and it's what we now see as the cosmic microwave background radiation. But that's not what we're talking about here. We're talking about photons trying to get out of our exploded star. While ionized hydrogen is opaque, neutral hydrogen is transparent in most wavelengths, and this recombination front, where the opacity changes, is known as the photosphere of the star, right? Where light is coming from, the layer the light is coming from, just like in the sun, that's the photosphere. And so because hydrogen is becoming neutral in the outer layers, the outermost layers, but it's still ionized below that, what we see is the layer down to where it's becoming neutral and therefore almost transparent, and the light is easily escaping after that point. So we see down to the ionization front, and that makes the photosphere. Once the hydrogen starts to recombine, photons from the hotter inner regions of the hydrogen envelope are able to escape, and we're able to see deeper into the star. And so here we've got initially the hydrogen envelope is fully ionized and only photons from the outermost regions can escape from the supernova. But on the right, as the supernova cools, the hydrogen recombines to its neutral form, and we're able to observe photons from successively deeper layers within the star. So we have, in the photospheres at about 5,000 Kelvin, not too different from the sun. And so here's the picture then. The photosphere is the 5,000 Kelvin line, which keeps moving inwards as the star cools overall. And so the inner part is ionized hydrogen that's opaque. The outer part is neutral hydrogen, which is transparent. In a type 2 supernova, the position of the photosphere corresponds to where hydrogen recombination is taking place. Since the temperature of recombination is constant, as the supernova expands and cools, the photosphere recedes into the star, and a plateau, the length of which is dependent on the depth of the hydrogen envelope, is created in the light curve. And so you get that plateau because of that presence of that photosphere, and it stays at about the same temperature, but it's shrinking because it's more materials cooling and it's moving inwards. And so it is getting dimmer because of the shrinking size of the photosphere, but not as fast as you would get as if that photosphere didn't form. And so that's why we have the type 2P plateau supernova. Questions, comments, observations? Never make a slide like this. I'm allowed to, but you're not. I'm not really allowed to. It's just that I wanted to have something to read and have it where you just, did you really want to write all that out while I was writing? No, you did not. You wanted to just have that you could read. So you're welcome. Okay. All right. So taxonomy. Here's our catalog of categorizing supernova. So we got type 2. That's your typical massive star supernova explosion. And we named supernovae types before we knew really the details of what was going on. And type Roman numeral 2 supernovae are ones that have strong lines of hydrogen in them. And a exploding massive star with the outer layers largely intact. Why, those outer layers are where it never got down into the core to fuse anything. So those outer layers are made mostly of what the sun's outer layers are made of today. So it's never going to go supernovae, but like all normal stars, why the sun's outer layers mostly are made of hydrogen. Yes, hydrogen. So you get strong hydrogen lines because look at all that hydrogen that's going to get blasted out here. So here's a nice strong H alpha line in the spectrum. Remember, that's the 3-2 transition in hydrogen, one of the Balmer series lines. So that's a type 2 supernova, a massive star, core collapse, iron core collapse supernova, where the hydrogen layers are still intact. And that's the typical situation. But wait, there's more, okay? So hydrogen lines, you got type 2, and then as we've seen, sometimes you get type 2P, plateau. Sometimes you get type 2L, linear, no plateau. Type 1 supernovae, by contrast, no hydrogen lines. So they were named, if you don't see hydrogen lines, it's a type 1. If you see lines of ionized silicon. So silicon, Roman numeral 2, how many electrons have been stripped off if it's Roman numeral 2? Because we're astronomers, the Roman numeral is related to, yeah, one more than the number of electrons that we move. So this is singly ionized silicon. If the supernova shows lines, spectral lines of singly ionized silicon, it's called type 1A. And now we know that's an exploding white dwarf. An exploding white dwarf supernova has ionized silicon lines. Why does it have silicon lines? What happens when the white dwarf explodes? It creates fusion not just of carbon, it fuses all the way up to the creation of iron. And what fuses into iron? Silicon, yeah. So silicon is also made in the explosion. And so we see silicon in the spectrum. of a type 2 supernova. So, sorry, type 1. So I said type 1 supernova, we see silicon. But in some supernovae that don't have hydrogen lines, we also don't see the ionized silicon lines. So those are called, depending on whether we see helium lines, type 1b, or no helium lines, type 1c. So again, this classification is based on just the spectrum, not the physical mechanisms. So just to be confusing, only type 1a is exploding white dwarfs. Type 1b and type 1c are massive star core collapse supernovae. So in other words, type 1b and type 1c are related more closely to type 2 than type 1a than they are to type 1. Well, they are type 1 from that standpoint. In other words, type 1b and type 1c are a different physical phenomenon than type 1a. They are much more similar to type 2 than they are to type 1a, to which they're not at all similar, basically. It's a completely different mechanism. Type 1, type 2, type 1b, and type 1c are all iron core collapse supernovae. What's the difference? Well, so again, type 1a exploding white dwarf. So this little picture is, oh, look, a red giant is spilling mass onto the white dwarf and adding mass to it. As we'll see, that will actually make a white dwarf shrink. The white dwarf decreases in size as it adds mass, because in order to achieve equilibrium, it's got to shrink to get the degeneracy pressure to catch up to the increased gravity within it. And so if enough mass is transferred and the white dwarf shrinks enough, it heats as it's shrinking, because gravitational potential energy is turning into thermal energy. It eventually gets to 600 million Kelvin, the ignition point of carbon. And does that go gently into this good night? No, it's degenerate. And so while it's not called this, why, it's a carbon flash. Right, and it blows itself to smithereens. That's your type 1a. It's really physically an exploding white dwarf supernovae. You see the silicon lines because the explosion produces silicon. One of the fusion projects in the exploding white dwarf is silicon, which makes iron too, but silicon is there. So we see those silicon lines. This is what happens with a type 1b. It's a supergiant star that, because of its strong stellar wind, has essentially stripped off the hydrogen envelope. And what you've got is the helium burning shell and the hydrogen burning shell and the core inside. You've stripped off the hydrogen outer layers. Sorry, no, you just have now you don't even have the hydrogen burning shell. It's all been stripped off. You're down to the helium burning shell, and below that you've made other elements heavier than helium. So in other words, you've stripped off the outer hydrogen layers. You're down to helium, down to the helium fusion shell. The core collapses and explodes. You don't see hydrogen because it all got removed by the strong stellar winds, but there's still helium there. And so you see helium lines in the spectrum. Does that make sense? That's the deal. You've lost the helium, but it's still a massive star, iron core collapsing supernova. No hydrogen like normal, because stellar winds have stripped off the hydrogen layers already. But there's still helium down there. Type 1c has no helium lines either. Guess what happens with them? What's happened with them? We got rid of the hydrogen lines by stripping off the hydrogens. How could we get an iron core collapsing and not blasting helium into space? Just think in terms of stripping off layers. Here we stripped off the hydrogen, hence no hydrogen lines, but there's still helium down there, so we have helium lines from that helium fusing shell. How could I get rid of the helium lines too? Strip off the helium too. Yeah. Type 1c is a supergiant with the outer hydrogen and helium removed. The iron core collapses and you get an explosion, but you don't get hydrogen or helium lines because you've stripped those off already. And so, hence, right, then Type 2 is that a white dwarf or did an iron core collapse? An iron core collapsed. Are you seeing hydrogen lines? Yes, because that's what makes it type 2. Okay, type 1, no hydrogen lines. Is that enough to say whether it was an iron core collapsing or a white dwarf exploding? Not yet. But if I see ionized silicon lines, what exploded? Well, what's the physical mechanism? A white dwarf blew up. Type 1A, a white dwarf blew up. Ah, I don't see hydrogen, but I do see helium. That's a type 1B. What blew up? Was it a white dwarf or did an iron core collapse? Iron core collapse. Yep. Ah, I don't see helium lines either, but I also don't see silicon lines, right? If I don't see silicon lines, it's not type 1A, it's not an exploding white dwarf. So no helium lines either. That's a type 1C. What collapsed? I just said it, but whatever. Repetition is key to learning. Did a white dwarf blow up or did an iron core collapse? An iron core collapsed. So in other words, in this whole picture, there's only one thing that's a white dwarf exploding. Type 1A, type 1A, type 1A. It's like, yeah, type 1A, type 1A, go type 1A. All right. If it's anything else, it's an iron core that collapsed. If I see hydrogen lines, the outer envelope is largely intact. If I don't, but I see helium lines, well, the hydrogen was blown off the star first, the outer hydrogen envelope, but not the helium inside that. So you can still see the helium fusing shell that was in there. If I don't even see the helium, well, even more stuff was removed before the core collapsed, and that's a type 1C. So in other words, physically speaking, there's white dwarf supernovae and core collapse supernovae, physically speaking. Only type 1A is white dwarf supernova. Everything else is a iron core collapse supernova. Okay. And one more quickie, and that is this comparison that I mentioned before, that type 1A, in terms of the optical luminosity, if you leave out the neutrinos, type 1A gets to be more than 1 billion times the luminosity of the sun in optical photons. Type 2 gets up to more like 600 million times or so. They're both fantastically bright, but type 1A are even brighter, optically speaking. And those are the ones that we've used to study the Hubble expansion of the universe, study the history of the expansion of the universe. And those are the ones that were used to infer the existence of dark energy, or at least that the expansion of the universe is accelerating, both because they're the most luminous type of supernovae at optical wavelengths where you can actually measure their output, and because they all have a similar mechanism. It's an exploding white dwarf, and there's not all exactly the same, but they're relatively similar to one another, so that we can use them as so-called standard candles. There's not as big a dispersion in their luminosities as there is for type 2s. And even with that dispersion, there's a correlation between the maximum brightness of a type 1A supernova, white dwarf supernova, and how long it takes to decay, and the decay rate along the curve. So it turns out that you can correct for that. And if all goes well, and this is something that's disputed because scientists have to question their assumptions, but if all goes well, they can be used as standard candles. They're all the same luminosity after you correct for it. And you can probe vast distances, billions of light years across the universe, because we can see them from billions of light years away. And more on that later when we get to cosmology, but that's kind of the big picture. So now we've blown up massive stars, and then next week we'll start talking about what low mass stars leave behind white dwarfs, and then we'll talk about neutron stars, what massive stars leave behind, and then after that
we'll talk about general relativity and black holes. Good stuff coming up. Yeah. The exciting stuff is coming, at least. I mean, it's all exciting to me, but I love general relativity and curved space-time and all that kind of stuff. So I'm looking forward to talking about all that. All righty. See you next time. If I did what? I would love to teach a GR course. I really would. Yeah. But yeah, the problem is we have all these courses we have to teach, you know, and so it'd be hard to fit that in. Yeah. I would love to teach a GR course is what it comes down to, but